So hi guys, so for today I'll be discussing the unit operation called fluidization. And with that, let us first differentiate unit operation from unit process. And for the main discussion, I'll be discussing the stages of fluidization, some important properties involved, and also the ergon equation and other formulas involved in the operation. So let's get started. So as future chemical engineers, some of us will be working in industrial plants. And in industrial plants, we'll be encountering different unit operation and unit processes. But what is the difference between the two? So from the Chemical Engineering Law of 2004, unit operation means the physical operation by which a desired step in an industrial process is conducted or controlled. On the other hand, unit process means the chemical change which is involved in the manufacture of industrial or consumer products or the treatment of industrial or chemical waste. So basically, kung moingon ta unit operation kay physical change, then when we say unit process it involves chemical change. And in here in the table below, here are some examples of unit operation and unit processes. So that maka clearly distinguish ta between the two. So in unit operation, we have kanang examples kay distillation, absorption, adsorption, fluidization, etc. And for the unit process, examples of which kay neutralization, oxidation reduction, saponification, nitration, etc. So next. So for today, we'll be focusing on fluidization. So what is fluidization? So, it is the process of transforming a bed of solid to a fluid-like state through an upward drag force of a liquid or gas that balances the weight of the individual particles. So, from the definition, transforming a bed of solid to a fluid-like state. So, the solid acts like a fluid. Thus, it tends to seek its own level and assumes the shape of its container, just like a gas and a liquid. So, in the figure below, it is an ion exchange na operation, and which actually kanang involves the fluidization operation since naaman siya fluidized bed column. So in here, our fluid is the wastewater. It is pumped to the purolite. Our purolite is our solid. Then in here, adsorption occurs in the purolite. So the purolite absorbs the calcium and magnesium. And after which, kung nakapass through na atong fluid sa purolite, our effluent will now become clean. Okay? So here are other examples of applications of fluidization. So we have reactors. This includes catalytic cracking of hydrocarbons, coal gasification, carbonization. Then our example ganiha, adsorption and desorption. And we also have solidification and granulation, and coating and biofluidization. Okay, next. So during the fluidization operation, the bed of particles undergoes different stages to form different types of bed or regimes. And this depends on the applied fluidization velocity of our gas or liquid. So as we can see here sa ato ang figure A, it is a diagram that shows the relationship between the pressure drop and bed height to the superficial velocity. And atong makita diri kay we have the this curve represents the bed height, and this curve represents the pressure drop. And we also have here the different stages, the fixed bed, fluidized bed, and mobilized bed. So, before the start of fluidization, our bed of solid is termed as fixed bed. And as the superficial velocity increases, at fixed bed, the bed of solid actually resists the force applied by our fluid. Mauna, as we can see here, since it resists the force applied by our fluid, mauna constant ang ato ang L, atong bed height. Ato makita diri na constant atong bed height. And at the same time, since there is resistance, that's why nag-increase ang ato ang pressure drop. So here, our pressure drop increases linearly. Then, as our superficial velocity increases pagyud, there will be such a time na the force applied by our fluid balances out the weight of our solid. It balances out. And at that point, the fluidized bed stage occurs. And the velocity at that stage, at the start of that stage, is actually termed as the minimum fluidizing velocity. And during this fluidized bed stage, we can see that our bed height is slowly increasing, or is increasing. There. And since no resistance occurs, kay ni-balance out naman ang force sa atong fluid sa weight sa ato ang solid. So, the pressure drop is now constant. Okay? Next, upon increasing again the superficial velocity, there will come a time that the terminal settling velocity will be achieved. So when we say terminal settling velocity, it is the maximum velocity of the solid particles. So at that time, it is the start of the mobilized bed. And during that time, constant na ang velocity. At constant velocity, or even at constant velocity kay our solid particles will move upward, continuously move upward, mao na mogawas na siya sa column. So again, we have fixed bed, na fluidized bed, and mobilized bed. So in summary, at fixed bed, it occurs from 0 to VOM, where VOM is the minimum fluidizing velocity. And as the superficial velocity increases, constant atong L, atong bed height, and increasing atong pressure drop. And in the fluidized bed naman, it occurs during sa start, and nag-start siya sa minimum fluidizing velocity to our terminal settling velocity. And at this stage, increasing ato ang bed height, and constant na ang ato ang delta P. Then lastly, sa itong mobilized bed, it occurs at the terminal settling velocity. Okay. So next, we have important properties involved in fluidization. With that, we have particle properties and bed properties. So for particle properties, we have particle diameter, which is the measure of particle size. We have sphericity, which describes how spherical the object is. We have true density, which is the density of our particle. Then next, for bed properties, we have bulk density, or the amount of mass per unit bed volume. We have external porosity or void fraction, which is the measure of space between the solid particles. Then here, so we have here the formula for computing the sphericity of the particle. So it is equal to the surface area of equivalent sphere over the surface area of the object or particle. So when we say equivalent sphere, let's take for example this object. So if ever kanang moldable pa lang ni kanina object, and ato ni siya gimold para mahimo siyang sphere, mao na ang equivalent sphere ani na object. Okay? But and how do we compute for the equivalent sphere? Diba, this object niya atong gimold siya into a sphere, then that means ang volume ani na object is just the same sa volume sa equivalent sphere. Yun siya. And with that, if given ta sa mga dimensions ani na object, like length, width, height, or even diameter, we can compute for the volume of the particle. And pwede na to siya equate sa volume sa equivalent sphere, which is ang volume sa sphere is equals to 4/3 pi r cube. And makakita ta og r. And from that r, kay makakompute na ta sa surface area sa ato ang equivalent sphere. Okay? And makakompute po ta sa surface area sa ato ang object gamit sa iyang mga given na dimensions. Okay? Next, we also have here the formula for bulk density, which is equal to the mass of the bed over the volume of the bed. Okay? Mass of this bed over the volume of this bed. We also have here the formula for computing the external porosity or void fraction. So it is equal to 1 minus bulk density over true density. And it is also equal to void volume over total bed volume. So ang void volume, mauna siya ang total volume sa wala gi-occupy sa ato ang mga solid particles. Kay within this kuan, kay di magyud na siya dili tanan spaces kay ma-occupy sa tong solid particles. So it actually has voids. And the total volume of that is the void volume. And the total bed volume, let us keep in mind na when we compute for the total bed volume, kay ang atong gamiton dili kani siya na height sa atong container. We will use this kaning L, bed height sa ato ang bed of solids. Okay? So, next. So, here is a table of kanang sphericity of miscellaneous materials. So, I got this from McCabe. And naapo daw ni siya sa Paris 6th edition. And it actually shows some directly na gyud ang sphericity sa mga materials. So, for spheres, cubes, and short cylinders, length is just equal to the diameter of the particle, and its sphericity is equals to 1. We also have here Rashig rings, mga burl saddles. I don't know unsa ni basta. But kanang pwede ra gyud ta makakompute atong sphericity gamit atong formula sa previous slide. Next. So we have the ergon equation. So this is the equation that is usually used for fluidization na mga problems. So mao ni siya. The ergon equation, where VO is the superficial velocity, delta P is the pressure drop across the bed, and L is the bed height. So for computing the minimum fluidization velocity, we can actually convert the ergon equation to a quadratic equation. So we can convert it to a quadratic equation. So we have here kanisha, this will be R A. Ay, stuck up akong kuan. This one kay katong x squared. And this one here will be our B. Kuya, kung kuan walay mouse. And this one will be X. Okay. And this part here, let me see. So see, it is kanang, pwede na to ma-convert ang itong ergon equation to a quadratic equation. And by that, pwede na nato siya i-directly o substitute ang mga values atong mga ma-compute ani na mga values sa atong calculator niya, maka-solve na siya directly sa minimum fluidization velocity. And take note, di ba na may duha ka answer. So we must take the positive answer, dili ang katong negative, ang katong positive na value. And actually this ergon equation uh, is divided into two. So first, okay, so once we isolate this part of the equation, it is actually called the Burke-Plummer equation. And kanus aman ta mo gamit aning Burke-Plummer equation. So it can be used for larger particles kani greater than 1 millimeter with a Reynolds number greater than 10,000, 1,000. So this equation is actually derived at turbulent flow. A turbulent flow siya gi-apply. So kung dagko gani atong, so when we have a problem niya dagko atong particles and at turbulent flow siya, pwede ra nato makuha atong fluidization, minimum fluidization velocity from this Burke-Plummer equation. Okay? So, isolating this part of the ergon equation, it is called the Karman-Kozeny equation. So, when man ta mo gamit aning Karman-Kozeny equation, so we use this for very small particles with Reynolds number less than 1. So, this equation is derived from a laminar flow. So, if ever gani nasa problem kay given ta og gagmay kina mga particles and at laminar pud ang iyang flow, we can actually derive the minimum fluidization velocity directly gikan ani na equation. So pwede na ta dili mo gamit aning taas kaayo. Pwede ra directly kani or kani. Okay? So, guys, mag-sample problem ta so that pwede na to ma-apply atong mga na-learn na formulas and equations. So, let me read the problem. So, a partial oxidation is carried out by passing air with 1.2 mole% hydrocarbon through 40 millimeter tubes packed with 2 meter of 3 millimeter by 3 millimeter cylindrical catalyst pellets. The air enters at 350 degrees Celsius and at 2 atm with a superficial velocity of 1 meters per second. What is the pressure drop through the packed tubes? And how much would the pressure drop be reduced by using 4 millimeter pellets? And assume porosity of 0.40. So, unsa man tong una buhaton ani? So, first, let's visualize the problem. So, naaday, partial oxidation occurs in tube. So, 40 mm na tube. So, with that, we have a tube here. Sorry sa drawing. Yeah, 40 mm tube. So, mao na 40 mm. So, kani siya, mao ni siya ang 40 mm. So, ang diameter niya kay 40 millimeter. Packed with 2 meter of 3 mm by 3 mm cylindrical pellets. So, mo ni na ay mga pellets din na cylinder. Batias akong kuan. Basta imagine na mga cylinder ni siya. Cylinder. Then, nag-occupy siya with 2 mm siya. 2 mm. 2 mm. Di na gibada. 2 mm. Ang size sa mga pellets kay 3 mm by 3 mm. Then, with that, na visualize na nato itong problem. Sunod, let's determine let's determine sa mga given. Okay, let's determine sa mga given. So, we have here, medium niya kay air. Have air. We also have the bed height of 2 meters. Ano siya? 2 meters. We also have superficial velocity of 1 meters per second. Superficial velocity of 1 meters per second. We also have We also have a kanang particle diameter of 3 mm and sphericity of 1. So ngano man ato ang particle diameter kay directly man ato na 3 mm and our sphericity kay 1. Itungod ang ato ang cylindrical pellets kay putot siya. Putot siya, so ang L is just equals to dp. Kay gikan ni siya sa ato ang katong table gani, katong sphericity of miscellaneous materials. If ever na given ta og short cylinders, pwede ra ta maka-assume na ang length sa atong cylinder is equal to the diameter of the particle. So mao na L is equals to dp, mao na ang L niya 3 mm man, so mao na atong dp kay 3 mm pod. Okay? Then ang sphericity, given ta og short na cylinder from the table, ang sphericity niya is just equals to 1. Okay? So there, we have L, we have VO, we have E, we have dP, and we have sphericity. And wala tay given na viscosity o density. So how do we compute this? So since given man ta og air, and given ta sa iyahang temperature and pressure, we can actually find the viscosity of air from our thermodynamic properties of air in Paris. Pwede ra nato na makuha dito. And ako nang gikuha mo na ang value niya is equals to 3.1456 times 10 to the power of negative 5 Pascal seconds. And dili ra kay siya layo sa value sa Mach cube kay 3 to the power 3 times 10 to the power of negative 5 Pascal seconds. Pero sa Paris kay 3.1456. Okay? And we can also compute for the density using the ideal gas law. So, we have density is equals to Pm, where M here is the molar mass, over RT. There, just plot the temperature and density. And take note na i-convert sa ang mole dito to kmol to cancel mga units. So 280 m, PA, cancel ang PA diri, mole, kmol, yeah, K. So we have kg na lang og meter cube ang nabilin. Okay, so sakto ra. For our density, upon computing it, we have our density is equals to 1.134 kilogram per meter cube. So for the first question, what is the pressure drop through the packed cubes? So we just substitute all the values na ato ang na-identify og nakuha sa previous slide to the ergon equation. So here is our ergon equation. Substitute tanan since it was already in SI units. Okay, wala na tayo lain i-convert pa. So with that, our delta P is equals to 18,301.13 pascals. Okay, mao na tong answer for A. Then for B, how much would the pressure drop be reduced by using 4 mm pellets? So with that, we just recalculate using a particle diameter equal to 0.004 m. And we just plot the values again to the ergon equation, except ato ra i-change kay ang kaning particle diameter. So it has been changed to 0.004 meters there. And with that, our pressure drop is equals to 12,619.96 Pascal. But we would not stop there, kaya ang atong gipangita kay reduction sa to ang pressure drop. So, percent reduction is equals to morning katong value from A. So we have 18,301.13 minus 12,619.96 ano siya? Over 18,301.13 times 100 equals to 31.04%. So our pressure drop upon the increase of our particle diameter, our pressure drop has been reduced to 31.04%. Okay, so mao na atong answer. So here are other formulas that can be used in fluidization problems. So we have particle Reynolds number. So it is equal to rho dp vom over mu times 1 over e. So mo ni siya ang particle Reynolds number if given ang minimum settling velocity. But if ever naatay velocity sa atong particle given, we can use the original na Reynolds number na equation katong rho dv over mu. Okay? Pero kani siya naaragyo 1 minus e sa ubos if ever minimum fluidizing velocity ang given or atong naa. Okay? Next, we can also compute for the terminal settling velocity, ut. And our ut can be, if ever in Stokes law regime mga ato ang mga particle, we have this equation for the ut. And if ever naa sa Newton's law regime atong particles, we compute for the ut using this formula. And take note, if the particle size is too small to be seen, assume Stokes law. Assume ani if kagmay gid kayo itong mga particles. Okay? And we can verify the terminal settling velocity by checking the particle Reynolds number. So here's the formula of the particle Reynolds number. So we have rho dp ut. So terminal settling velocity natong gigamit diri over mu. So, for example, kano sa man ta mo verify? So, for example, natay problem nya atong gisolve ang ut nya feel nato nagamay gyud kay itong kato na particle. So, mao na atong gigamit pang compute sa ut kay ang Stokes law. Mao na atong gi-compute siya. Mao na natay makuha na ut. Nya ato siya i-verify if ever sa Stokes law bagyud siya na terminal settling velocity. So, ato siya i-verify, ato i-plot ato ang substitute atong ut diri, makakuha ato Reynolds number. So, if ever gani na ang atong nakuha na Reynolds number kay for example 1,000 or 2,000, that means sayop atong gikuha na terminal settling velocity. It is not under the Stokes law regime, but it is under the Newton's law regime. Okay? So, mao ni pag-verify if ever sa sakto ba atong gikuha na terminal settling velocity. Can verify it again by using the Reynolds number. Okay? So, I have here kanang pwede rin ninyo if wamoy lingaw guys, ansiran ninyo an exercise. So, let me read the problem. So, we have a bed. A bed is composed of particles that have a density of 1.31 gram per cubic meter and an average size of 12.8 millimeters. Assume spherical beads and a porosity equal to 0.3. Calculate the following. A. Minimum fluidizing velocity using water. B. Particle Reynolds number at the start of the fluidized bed stage. And C. Terminal settling velocity in meter per second. And I have here yung answers. So, sa pag-compute na to sa minimum fluidizing velocity, we can use the Ergun equation katong quadratic form. But, katong matanawan diri kuha man gyud kaayo atong mga given. So, ato na diri kay we have particle density, we have dp, and em watay katong sphericity, density sa atong fluid o viscosity sa atong fluid. But, however, naka-state man diri na spherical beads. So, check na ato ang sphericity, it is equals to 1. Kay spherical naman ato ang solid. And for our kanang fluid density and viscosity, we can assume, and since water man siya, we can assume that it is equals to, density is equals to 1,000 kg per meter cube, and for our viscosity, it is equals to 0.001 Pascal second. Okay? So, nanatanan given, so mo na, makakompute na ta sa itong fluidizing velocity. Then, for the particle Reynolds number, since makakuha man ta og VOM diri sa A, so makakompute na po ta sa itong particle Reynolds number at the start of the fluidized bed stage. Okay? And also, makakompute po ta sa itong terminal settling velocity. And pwede na ito ma-verify if ever sakto ba itong pag-compute sa terminal settling velocity using the particle Reynolds number. Okay? So, kalingawi lang na ninyo guys. So, lastly, where can we find fluidization in the Paris and its mga equation and formulas? So, I have tabulated here kung asa ninyo siya makitaan sa Paris. And you can use this para pwede nyo magsugod mo tabs, or highlight sa ani na mga equations. Okay? So, that is all. Thank you for listening and bye-bye!